Hello, my name is Ethan Chinnis, and this is lab number 2, motion of a falling object. The purpose of this lab is to track the movement of a falling object from rest and compare it to one that would theoretically have no drag to see the effects of drag on the object. The physics principles used in this lab were F equals ma, which is force equal to mass times acceleration, and the force of drag, which is equal to negative b times speed squared times the velocity unit vector. And the result is that when an object reaches a certain velocity, which is called the terminal velocity, the object will have gravity force is equal to the force of drag, which causes it to have zero acceleration and thus cease to increase in velocity and have constant velocity. Newton's second law, F equals ma, or Fg is equal to mg in this case, is how we use the force of gravity on our object. In the drag equation, F drag is equal to negative b times the speed squared times the unit vector is how we find the force of drag, and thus the time at which Fg is equal to F drag and the velocity at that time, which is our terminal velocity. And the terminal velocity is the time at which our momentum of our force of gravity is equal and opposite to the air resistance or drag, thus causing zero acceleration and a constant velocity. In the experiment, the system is the paper ball, the surroundings is the air, our initial velocity is 0 meters per second, and our mass of the paper ball, which I throw down, is 0.0045 kilograms. Our b, or which is part of the drag coefficient, is negative 0.008, and the height at which I drop the paper ball from is 2.4003 meters. Here we can see the graph curves down until eventually reaches a constant slope, or a approximately constant slope, and that is when we hit our terminal velocity. And here's the code. So the code with no drag, as we can see here, the ball's mass initial position is the height, and the velocity starts from 0, and our net force is just mass times gravity times our unit vector, which in this case, as we can see here, we can see that the graph is just a constant curve downwards, which means it constantly increasing velocity in the negative direction. Meanwhile, with drag, it's relatively the same code, except for the fact that when our net force is now subtracted the force of drag, which is negative v times velocity squared times the unit vector of velocity, thus having a force in the other direction. As we can see here, it is curved until it reaches a constant velocity at some point, which is our terminal velocity. In comparison, the experimental versus the model with drag both reach a point around here where they hit terminal velocity and thus have a constant velocity the rest of the way down. Meanwhile, with no drag, we have constant acceleration, which causes a constant increase in velocity. So terminal velocity, or what does it mean with our velocity with no drag, we can see our velocity constantly decreases in the negative or increases in the negative direction. Meanwhile, when we add drag, at some point our velocity evens out to become a constant velocity. This is because the force of drag, when velocity increases, since the force of drag has speed squared, meanwhile the force of gravity, or our momentum, just has velocity, at some point the force of drag will increase to equal the force of gravity, causing it to be 0 and have a constant net force of 0. If the object is thrown, it does start out with a higher velocity, however it slows down back to the terminal velocity. This is because since v is squared in our drag equation, while it's just a v in our momentum equation, the velocity, the force of drag increases much faster than the force of momentum of gravity. This causes force of drag to be much higher than gravity here and cause it to slow down because it's actually being pushed upwards. However, once it slows down to equal the force of gravity, it once again reaches this constant velocity. As you can see here, the graph curves a little bit and quickly reaches that constant velocity, slows back down to that. And that is all.